Hello everyone, I am Dr. VRAO-PHYSICAL. Today I am here with another concept in thermodynamics, that is Gibbs free energy, equilibrium and equilibrium constant, right? That is, we are going to discuss the relation between Gibbs free energy, equilibrium and equilibrium constant, right? Relation between Gibbs free energy G and G, equilibrium and equilibrium constant. Right? Right. We know that for a chemical reaction to occur spontaneously, Gibbs free energy change should be negative. I repeat, we know that for a chemical reaction to take place or for a chemical reaction to occur spontaneously, Gibbs free energy change should be negative. Then what is the relation between Gibbs free energy change and equilibrium constant, right? So to understand the relation between Gibbs free energy and equilibrium constant, let us consider the reversible reaction. Let us consider a reversible reaction. A gives rise to B and B gives rise to A, right? Okay. So from here onwards, I use the term Gibbs energy instead of Gibbs free energy, right? I use the term Gibbs energy instead of Gibbs free energy, right? So A gives rise to B, it is a reversible reaction, right? With the progress of the reaction, we know that for a chemical reaction to occur spontaneously, Gibbs free energy change should be negative. That is, with the progress of this reaction, Gibbs free energy decreases whether we start from reactants or from products, right? So with the progress of the reaction, that is, A is becoming B, with the progress of the reaction, Gibbs free energy or Gibbs energy decreases whether we start from reactant or from product, right? That means with the progress of the reaction, Gibbs free energy of the reaction mixture, varies with the composition of the reaction mixture, right? So with the progress of the reaction, Gibbs energy of the reaction mixture varies with the composition of the reaction mixture. That is, what is the composition of the reaction mixture? Okay, let us understand. For example, this reaction starts with initially 10 moles of A. This reaction starts with 10 moles of A. And this reaction take 10 minutes to complete, right? For example, initially it is started with 10 moles. So for 1 minute, for example, say after 1 minute, in this 10 moles of A, 1 mole of B is formed. Okay, this is for after 1 minute, right? And after second minute, after 2 minutes of reaction progress, this would become 9, or this would become 8, and this would become 2, right? After 3 minutes, this would become 7 moles and this would become 3 moles. After 5th minute, this would become 5 moles and this would become 5 moles. right? After 7th minute this would become 6 moles and this would become that is this would become 4 moles and this would become 6 moles. That is, with the progress of the reaction, Gibbs free energy or Gibbs energy of the reaction mixture decreases, Gibbs energy of the reaction mixture decreases with composition of the reaction mixture. So, composition, how the composition varies, if we start with 10 moles of A, after 1 minute of reaction progress, 1 mole of A decreases and that 1 mole is formed in the form of B. Okay, after 3 minutes 7 moles and A becomes A would become 7 moles and 3 would become 3 moles. Right. This means that with the progress of the reaction, Gibbs energy decreases, or that is Gibbs energy of the reaction mixture decreases with the composition of the reaction mixture, Okay, but a stage comes with the progress of the reaction, a stage comes where composition of the reaction mixture becomes constant, right? With the progress of the reaction, composition of the reaction mixture becomes constant. Right? Becomes constant. So, what is the composition? This is a reversible reaction, and the composition, that is concentration of B by concentration of A. Okay, that becomes constant. For example, after 5 minutes of the reaction progress, A becomes 5 moles and B becomes 5 moles. That is composition of the reaction mixture, that is reactants and products becomes equal, and the composition, the ratio of the composition of the reaction mixture, that is concentration of B to concentration of A, that becomes constant. Okay, and when that reaction mixture becomes constant, that indicates the equilibrium. Therefore, we can understand that when the reaction mixture becomes constant, equilibrium established, or when equilibrium is established, composition of the reaction mixture becomes constant. Right, becomes constant. So this constant, when this composition of the reaction mixture becomes constant, and this constant is called equilibrium constant. Already we know that equilibrium constant, it is a ratio of concentration of products to concentration of reactants, right? That is the equilibrium constant. Therefore, we can understand that when the reaction mixture becomes constant, when the composition of the reaction mixture becomes constant, reaction reaches the equilibrium, or when the equilibrium is reaches, the composition of the reaction mixture becomes constant. Right, when that is with the composition of the reaction mixture, Gibbs energy changes. That is okay, you should keep one point in your mind, that with the composition of the reaction mixture decrease, Gibbs energy also decreases, and the composition of the reaction mixture becomes constant, then Gibbs free energy becomes reaches a certain value, that is, it reaches a minimum value. Okay, reaches a minimum value. Okay, therefore, when we plot the Gibbs energy decrease, against change in the reaction composition, and the composition of the reaction mixture, that would give you a graph. Okay, that graph is like this, right? For example, when we plot the when we plot the Gibbs energy, okay, when we plot the Gibbs energy, Gibbs energy with the composition of the reaction mixture, with the composition of the reaction mixture, composition of the reaction mixture. Okay, a graph of this type is obtained, for example. Okay, right. So this is the Gibbs energy of standard Gibbs energy of reactants, standard Gibbs energy of the reactants. Okay, standard Gibbs energy of the reactants. Okay, it is a certain value. With the progress of the reaction, when we plot the Gibbs energy against composition of the reaction mixture, variation of composition of the reaction mixture with the time, okay, that standard Gibbs energy of the reactant decreases and reaches a certain value and then increase. This is standard Gibbs energy of the products. Standard Gibbs energy of the products. With the progress of the reaction, Gibbs free energy of the reactants decreases and reaches a minimum Gibbs energy, that is at equilibrium mixture, at equilibrium composition, or when the composition becomes constant, when the composition of the reaction mixture becomes constant, Gibbs energy reaches a minimum value, okay, minimum Gibbs free energy or minimum Gibbs energy reaches a minimum value. Okay, for example, if the reaction, when we consider the reaction from products to reactants, that is the same graph, but that starts with here it starts with okay, if we consider the reaction of products to reactants, that would be like that, right? So that is dashed lines. To understand the graph, I represent with dotted lines, right? Okay, so reaction Gibbs energy reaches a minimum value. Gibbs energy reaches a minimum value, and okay, so when plot is drawn between Gibbs energy and composition of the reaction mixture, okay, this equilibrium composition reaches a minimum Gibbs energy, Therefore, we can conclude that with the reaction progress, composition of the reaction mixture becomes constant when the equilibrium is established, or when the equilibrium is established, composition of the reaction mixture becomes constant, where Gibbs energy is a minimum, that is called minimum Gibbs energy of the reaction mixture, right? Okay, so but what is the relation between Gibbs energy and equilibrium constant? That is the relation between equilibrium and Gibbs energy. Now let us consider the relation between Gibbs energy and equilibrium constant. For example, okay, when Gibbs energy minimum of the reaction, this is called Gibbs energy minimum. Okay, this is the scale of Gibbs energy. This is the Gibbs energy minimum. When the Gibbs energy minimum lies close to the products, if the Gibbs energy minimum lies close to the products, that means this equilibrium mixture strongly favors products. I repeat, when the Gibbs energy minimum lies close to the products, then equilibrium mixture strongly favors products. That means reaction goes to completion. Reaction goes to completion. When the reaction goes to completion, what we obtained? Products. The concentration of the products becomes more than concentration of reactants. Therefore, what we define K is concentration of products by concentration of reactants. Okay, when the Gibbs energy minimum lies close to the products, then equilibrium mixture favors products, that is concentration of products is more than concentration of reactants. So in this ratio, numerator value is more, therefore K value is greater than 1 or greater than 1 or greater, K value is greater than 1. That is when equilibrium, when Gibbs energy minimum close to the products, equilibrium mixture favors products, that is reaction goes to completion and concentration of products is more than concentration of reactants. Okay, that is, in such case K is greater than 1, right? That is equilibrium constant is greater than 1. For example, this equilibrium mixture, for example, if Gibbs energy minimum lies close to the reactants, then equilibrium mixture favors reactants. What does it mean? It means that reaction does not proceeds much. Because Gibbs energy minimum close to the reactants. When Gibbs energy minimum close to the reactants, there is more Gibbs energy, but for reaction to occur spontaneously or reaction to occur, Gibbs energy should be decreases. Here the Gibbs energy is lies close to the reactants, When Gibbs energy lies close to the reactants, this equilibrium mixture favors reactants. That is, what does it mean? It means that reaction does not proceeds much. That is, reactants or remains as reactants. Products are not formed. In such case, in this ratio, this denominator value does not change. This denominator value is more. That is why? Because reactants or remains as reactants. Okay, so in this ratio, denominator value is more than numerator value. In such case, K value is less than 1. Okay. For example, if this Gibbs energy minimum lies halfway between reactants and products, that is, this Gibbs energy minimum is lies halfway between reactants and products, that is, it is the center of the reaction block, that is, here it is the center, and the Gibbs energy minimum is center, that is lies halfway between the reactants and the products, then this ratio becomes a constant, then K is equal to 1, because in this case concentration of products is equal to concentration of reactants becomes equal, therefore K is equal to 1. Okay, therefore this is the relation between Gibbs energy and equilibrium. When equilibrium reaches, Gibbs energy is minimum. Okay, when what is the relation between Gibbs energy and equilibrium constant? If Gibbs energy minimum lies close to the products, that favors the products, that means K value is greater than 1. If Gibbs energy minimum lies close to the products, that favors products, reactants, that means the reaction does not proceed much. In such case, K less than 1. If Gibbs energy minimum lies halfway between reactants and products, then in this ratio products and reactants are becomes equal, therefore K is equal to 1. So this is the relation between equilibrium, Gibbs energy, equilibrium and equilibrium constant, right. Okay, let us derive the mathematical derivation between Gibbs energy and equilibrium constant. Right. Now let us see the relation between Gibbs energy, standard Gibbs energy change and equilibrium constant. From the previous classes, we know that the relation delta G is equal to delta G naught plus RT ln Q, where Q is the reaction quotient for the reaction A gives rise to B, reversible reaction. Okay, so RT ln Q, where Q is the reaction quotient, and when the equilibrium reversible reaction reaches equilibrium, that is at equilibrium, when the reaction reaches the equilibrium, at equilibrium, Q equal to K, that is Q reaction quotient is equal to equilibrium constant, and delta G is equal to 0, that is okay, change in Gibbs energy is 0. Okay, if we substitute in this equation delta G naught, standard Gibbs energy change, plus RT ln K, right. So this is equal to delta G naught equal to minus RT ln K, right, minus RT ln K, right. Okay, so and when delta G naught, when we multiply with the negative sign, that is RT ln K, so that is minus delta G naught by RT is equal to ln K, and K is equal to e power minus delta G naught by RT, Okay, for example, if you this is the relation between K and G naught, okay, and moreover there is another relation, that is right, and one more relation between these two, that is and when K less than 1, delta G naught is greater than 0, that is greater than 0. Okay, delta G naught greater than 0. When will be the K less than 1? When Gibbs energy lies close to reactants. In such case, K less than 1. When K less than 1, delta G naught greater than 0. Okay, when K greater than 1, delta G naught less than 0. When will be the K greater than 1? When Gibbs energy minimum lies close to the products. In such case, K greater than 1, then delta G naught less than 1. Delta G naught less than 0, that is negative, that is spontaneous. Okay, in such K less than 1, delta G naught greater than 0, that is non-spontaneous. Okay, so I hope you understand this concept. If you really understand this, you please extend your support by like, share, comment and subscribe. Okay, thank you for watching.